Hello everyone, good evening. This is lecture number 9 of linear algebra. If you haven't watched all the previous classes, I strongly recommend you to watch all the previous classes before getting into today's class, right? So this is part 3 of basis and dimension. The previous classes we are discussing about basis and dimension, right? The previous class we have talked about how to find the basis and dimension for the solution space of homogeneous system, right? Yes. So in this class, we're going to prove one theorem. We're going to prove one theorem based on dimension of W1 plus W2. So after that, based on that theorem, we're going to do problems. Right? So this is very important theorem, concept point of view. So you try to understand the theorem, right? It will be slightly vague for you to understand, but try to understand the theorem. Based on the theorem, we will do more problems, right? So problem is more important than theorem when compared to the previous trends of UPSC. They are giving more importance to problems than theorem, especially in linear algebra. So let us try to put theorem first, and then we will do some problems based on this theorem, right? Okay. So before getting into the theorem, first I want to start with one note. So what that note says is every linearly independent subset of a vector space is either a basis or it can be extended to form a basis. That's what it says. So first I'll start with one note and then we will prove the theorem, right? So what this note says is, every linearly, every linearly independent, subset of a finitely generated vector space of a finitely generated vector space. So every linearly independent subset of a finitely generated vector space is either a basis of V, or it can be extended to form a basis, or it can be extended to form a basis, right? This is obvious, right? See, for example, let us consider V to be equal to 1 comma 0 comma 0, and let us take 0 comma 2 comma 1. Right, now you can see these two vectors are a linearly independent subset of, let us take V to be a subset of R3. Now you can see these two vectors are linearly independent, right? Clearly these two are linearly independent only because one cannot be written as the other linear combination. But what is the dimension of V? Dimension of V is 2 only because it has only two linearly independent element. So even though it is linearly independent element, it is not basis, because for to be a basis, it has to be linearly independent and it has to span the entire vector space. That is, L of S has to be equal to V. Linear span of this has to be equal to R3, right? But let us consider S, right? So let us consider S instead of V. Let us consider S. So even though, but the linear span of S is not equal to V, because the linear span will cover only two dimension. It has only dimension 2, right? Dimension, but V has dimension 3. So even though it is linearly independent, it is not a basis because the dimension is not matching. So even though it is not a basis, we can extend it to form a basis, right? By adding some elements. For example, if I add one more element, 0 comma 0 comma 1, now we can see these three are linearly independent and dimension is also 3, so it forms a basis. So every linearly independent subset of a finite generated vector space is either a basis. Now we can say this is a basis. Even if it is not a basis, we can extend it to form a basis by adding some elements. That what this note says, right? Is it clear? Right? Is it clear? Okay. It can be extended. It can be extended. Can be extended. Form a basis, right? So we need to add some more vectors. We need to add some linearly independent vectors, right? We need to add some linearly independent vectors so that the dimension will be equal to 3 and then dimension, it will span entire V also, right? We need to add a vector so that the three vectors are linearly independent. That way you need to add, right? So every linearly independent subset of a finitely generated vector space, either a basis of V or it can be extended to form a basis, right? So this is a very important note. So now what we will do is we will see this, we will see a theorem. So let us try to understand this theorem, right? Let us try to understand the theorem. We will do some problems based on after that theorem, right? Okay. So theorem. So what this theorem says is if W1 and W2, if W1, uh, if W1 and W2 are two subspaces, if W1 and W2 are two subspaces of a finite dimensional vector space of A, if W1 and W2 are two subspace of a finite dimensional vector space, then dimension of W1 plus W2 is same as dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So this is what this theorem says, right? If W1 and W2 are two subspaces of a finite dimensional vector space, then the dimension of W1 plus W2. So you know what is W1 plus W2, right? So W1 finite dimensional. We already defined all the terms, right? You know what is W1 plus W2. So W1 plus W2 is nothing but W1 plus W2 is nothing but what? Linear sum of subspaces, right? Linear sum of two subspaces. Okay. So if W1 and W2 are two subspaces of a finite dimensional vector space, then dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2, right? That is nothing but and the number of elements, the basis of W1 plus W2 is same as number of elements, the basis of W1 plus number of elements in the basis of W2 minus number of elements in the basis of W1 intersection W2. This is what this theorem says, right? Okay, see, dimension is nothing but total number of elements in the basis, right? For a finite dimensional vector space. Okay. So we'll try to prove the theorem. So it'll be lengthy, but let us try to understand, right? It will take some time. Okay. So uh, let us start with the assumption that uh, let dimension of W1 intersection W2 to be equal to k. So let us assume that this dimension is k. That means W1 intersection W2 has k elements in the basis, right? Has k element in the basis. So let us take S. Let us take S to be equal to gamma 1, gamma 2, gamma 3 and so on up to gamma k be a basis of be a basis of W1 intersection W2, right? So we have, I assume this dimension is k. That means it has k element in the basis. Let us say those elements are gamma 1, gamma 2, gamma 3 and so on a basis of W1 intersection W2. Now this S is linearly independent, right? This set S is linearly independent. Set S is linearly independent, right? And S is a basis for W1 intersection W2. So these vectors will be belongs to W1 as well as belongs to W2. but need not be a basis, right? Surely these vectors are linearly independent, right? Surely these vectors are linearly independent, and these vectors are basis for W1 intersection W2. That means these vectors will be in W1 as well as these vectors will be in W2, because these vectors belongs to intersection of both. But it is not it need not be that that these vectors forms a basis for W1 and a basis for W2. As of now, these vectors forms a basis for W1 intersection W2, but these vectors are linearly independent, will be in W1 as well as will be in W2, but need not be a basis for W1 and W2 separately, right? Okay. Since this set S is linearly independent and this yet S is contained in W1, right? So therefore S can be therefore S can be extended to form a basis for W1, right? Okay, these vectors will be in W1, but these independent vectors need not be a basis. Even though it is not a basis, since it is linearly independent, it can be extended to form a basis. We can add some vectors, right? So this S can be extended to form a basis for W1. So let basis for W1 be, let us take a basis. See, already we have these vectors gamma 1, gamma 2, gamma 3 and so on up to gamma k. So we'll add some vectors, right? So we'll add some vectors so that this will be a basis for W, so that this will be a basis for W1, right? So we'll try to add a vectors. So let us say alpha 1, alpha 2 and so on up to alpha m. That's the basis of W1 B, right? Then what is the dimension of W1? Already here we have k elements and then we are adding m elements. Therefore, the dimension of W1 is k plus a. Now, similarly, these vectors is also in W2, but these are linearly independent vectors in W2. It necessarily need not be a basis for W2. Even though it is not a basis for W2, these are linearly independent vectors. I can add some vectors so that these vectors will be a basis for W2, right? Uh, similarly, similarly, the above, the above set S is contained in W2. The above set, similarly, the above set S is contained in W2 because this S is in W1 intersection W2. So these independent vectors will be in W1, need not be a basis, even though it need not be a basis for W1, extending with alpha 1, alpha 2, alpha m. And similarly, this S is contained in W2. Therefore, S can be extended form a basis for W2, right? So let the basis for W2 be, see, already we have gamma 1, gamma 2 and so on up to gamma k. Now I'm going to extend with beta 1, beta 2, beta 3 and so on up to beta 3. Then the dimension of W2 will become what? Dimension of W2 will become, already we have k elements. I'm adding t elements. So this will be k plus t. So dimension of W2 is k plus t. Is it clear up to now? See, as of now, what I did is I have assumed that the dimension of this is k. So that means the basis will have k linearly independent vectors, and also these linearly independent vectors will span W1 intersection W2. So S is equal to gamma 1, gamma 2, gamma 3 and so on up to gamma k be a basis for W1 intersection W2. Now this independent vectors belongs to W1 intersection W2. That means these independent vectors will be belongs to W1. But these independent vectors belongs to W1 does not necessarily mean this is a basis. Even though this is linear, even though it is not a, even though since it is linearly independent, I'm adding some vectors so that this will be a basis for W1. Similarly, these vectors belongs to W2. Even though these does not form a basis for W2, I can add some vectors, these independent vectors, so that it will be a basis for W2 also. So as of now, you can see I have a basis for W1 plus W2. I have a basis for W1. I have a basis for W2. Number of elements in W1 is k plus m. Number of elements in W2 is k plus t. Right? Yes. Now what I'm going to do is, um, now what I'm going to do is, yes. Now what about, now, now what about the dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. What about this? So what is dimension of W1? So dimension of W1 is, already we have k elements and then m. So this will be k plus m plus dimension of W2. So dimension of W2 is k plus t minus dimension of W1 intersection W2. So that is by assumption is k. So this will be k plus m plus t, right? So now we will prove that, now we will now we will prove that dimension of W1 plus W2 is also equal to k plus m plus t. Right? See, I'm just doing LHS equal to RHS. So I have assumed this is equal to k, right? Now I have this turns out to be k plus m. This turns out to be k plus t. Sorry, sorry. I have assumed this to be equal to k, right? Sorry. So dimension of W1 intersection W2 is k, right? I think I have said dimension W1 plus W2 is k. Sorry, I've assumed that dimension of W1 intersection W2 is k. So let S is equal to gamma 1, gamma 2, gamma 3 and so on up to gamma k be a basis for W1 intersection W2. So this S is independent. These are clear. So what I'm going to do is, I have assumed this dimension to be equal to k, and I have found the dimension for these two with respect to this. So I have found the dimension for entire thing, that turns out to be k plus m plus t. Now we will prove that dimension of W1 plus W2 is equal to k plus m plus t. Right? Okay. So proof. So how I'm going to prove is, we claim just a minute. I'll just recheck the video. A minute. Yes. So I think in the beginning of proof, I said that when I'm explaining, I said this. I said that this is equal to k. Sorry, dimension W1 intersection W2 is k, right? So yes is so that means I'm assuming this dimension is k. That means it will have k elements, k linearly independent elements will span the entire vector space, right? So, and this is similar, right? And this is easy, right? So these are linear independent elements belonging to W1 intersection W2. That means these elements will be in W1. So that means these are linearly independent elements belongs to W1. So that means even though it is not a basis for W1, I can extend to form a basis. So let the extension vectors be alpha 1, alpha 2 up to alpha m. So m vectors I have extended with k vectors. So dimension W1 is k plus m. And similarly, the above set, this set is contained in W2 also. This is a linearly independent vectors. So I'm extending to form a basis for W2. That extension vectors be beta 1, beta 2, beta 3 up to beta t. Dimension is k plus t. So I assumed this dimension is k, and I have found dimension of W1 and dimension W2 in terms of k, and I am finding these quantity, which turns out to be k plus m plus t. Now I need to prove dimension of W1 plus W2 is also equal to k plus m plus t. Right? Okay. Yes. So we'll continue. I just rechecked the video whether I have made mistake or not. So we did correct only, but I'm explaining. I said this is equal to k. So this is equal to k. Okay. Now we claim that, and now what is our aim? Our aim is to prove that dimension of W1 plus W2 is k plus m plus t, right? K plus m plus t. Okay. So that means we claim S1 is equal to what is which has dimension k, has dimension k. So gamma 1, gamma 2 and so on up to gamma k, which has dimension m. So alpha 1, alpha 2 and so on up to alpha m, which has dimension t, beta 1, beta 2 and so on up to beta t. Now I'm going to say that this set forms a basis for W1 plus W2. If I say that, the proof will be over. Yes or no? Okay, I need to form. See, I need to show two things. First, this set S1 is a basis for W1 plus W2. If I say that this set is a basis for W1 plus W2, see what is gamma 1, gamma 2, gamma k? This is the basis for W1 intersection W2. And what is alpha 1, alpha 2 up to alpha m? These are the extension vectors of W1, so that it will be a basis for W1. And what is beta 1, beta 2 up to beta t? These are the extension vectors of um, W2, so that it is a basis for W2. Now, if I say that these vectors forms a basis for W1 plus W2, then what about the dimension of this? It is nothing but k plus m plus t. We'll prove that this is equal to this. So I need to show this is a basis for W1 plus W2. So to show this is a basis for W1 plus W2, I need to show two things. First, I need to claim that this set S1 is linearly independent, and I need to prove that linear span of S1 is equal to V. That's it. So if I show this, then the entire theorem will be over, right? Okay. So I'm going to show two claim one. So claim one is S1 is linearly independent. So I need to show two things. First thing is we need to show S1 is linearly independent, and we need to show L of S1, linear span of S1 is equal to V. Right? Okay. So we'll prove S1 is linearly independent. So that means you add scalars, make a linear combination of these with scalars. You need to show that all the scalars are zero, right? Okay. So what we'll do is C1 gamma 1, C2 gamma 2, C3 gamma 3, and so on up to K gamma K, plus I'm just multiplying scalars A1 alpha 1, A2 alpha 2, and so on up to AN alpha m or AM alpha m, plus P1 beta 1, P2 beta 2, and so on up to Pt beta t is equal to 0. That means we need to prove what? We need to prove these C1, C2 and so on up to Cn, A1, A2 and so on up to Am, B1, B2 and so on up to Bt all are equal to 0. So if I see, these are vectors, I'm just multiplying scalars C1, C2, C3, Cn, A1, A2, A3 and so on to Am, B1, B2, B3 and so on up to Bt. I need to show that if all these scalars are 0, then I can say that this set is linearly independent vectors, right? Now I need to show that all these vectors are 0. Okay, so we will show that. Um, so now, so write it down and then I'll explain, right? Okay, now B1 beta 1, B2 beta 2 and so on up to Bt beta t equal to minus C1 gamma 1, C2 gamma 2 and so on up to understand Ck. So Ck gamma k plus A1 alpha 1, A2 alpha 2 and so on up to Am alpha m, right? Okay. Now C1 gamma 1. Okay. Now you can see that these vectors belongs to W1. Yes or no? These vectors belongs to W1. Yes or no? Because W1 is what? Gamma 1, gamma 2, gamma 3, alpha 1, alpha 2 up to alpha m. That means these vectors belongs to Wm because this is a linear combination of elements of basis of W1, right? Because it is a linear combination of basis vectors of W1. So it will be in W1. And these vectors belongs to what? These vectors belongs to W2. Yes or no? Because beta 1, beta 2 up to beta t. So these are vectors in W1, right? So sorry, W for W1. Okay, these are vectors in W2, right? Yes. So these are vectors in W2, right? And can I say this beta V1 beta 1, V2 beta 2 and so on up to Bt beta t belongs to W1 intersection W2, because you can see this vectors is W2 and that is equal to W1. That means already this vectors belongs to W2 and already this vector belongs to W1. That means this also belongs to W1. This belongs to W2 as usual. That means this vector belongs to W1 intersection W2. Yes or no? So this B1 beta 1, B2 beta 2 and so on up to Bt beta t belongs to W2, as well as this is equal to this and this vector belongs to W1. That means this vector belongs to W1. That means B1 beta 1, B2 beta 2 up to Bt beta t belongs to W1 intersection W2, right? So that means this vector, so that means, so thus we have so that means this vector can be expressed as a linear combination of basis elements of W1 intersection W2. That means B1 beta 1, B2 beta 2 and so on up to Bt beta t can be expressed as a linear combination of elements of W1 intersection W2. So dimension of W2 is k. So these are the basis elements. This can be written as some T1 into gamma 1, T2 into gamma 2 and so on up to Tk into gamma k. Tk into gamma k, right? So as of now, I have said that these vectors belongs to W1 intersection W2. That means these vectors can be written as a linear combination of basis elements of W1 intersection W2, right? Okay. So that means can I write B1 beta 1 plus B2 beta 2 and so on up to Bt beta t minus T1 gamma 1, T1 gamma 1 minus T2 gamma 2 and so on up to Tk gamma k is equal to 0, right? But see what I'm doing is, see, but we know beta 1, beta 2 and so on up to beta t, right? And gamma 1, gamma 2 and so on up to gamma k are linearly independent, right? Because we know that these are linearly independent vectors, right? These beta 1, these beta 1, beta 2, beta 3, beta t and gamma 1, gamma 2, gamma 3 independent vectors. So linearly independent vectors. So that means what? All the scalars has to be 0. That means therefore therefore we must have we must have B1 equal to B2 equal to and so on up to Bt to be equal to 0. Okay, what is our aim? Our aim is to show these all are 0. Now, as of now, I proved this part B1 equal to Bt equal to Bt. All the Bi's are 0. I proved this part, right? I proved this part. Okay. Now, similarly, I need to prove what? These two parts. All the C's and all the A's are 0. We need to prove, right? So, putting these values of B in equation number 1. So, let us call this as star, right? So, put this in star. We have C1. We have what? C1 gamma 1 plus C2 gamma 2 and so on up to Ck gamma k plus A1 alpha 1, A2 alpha 2 and so on up to Am alpha m equal to 0, right? And similarly, we have gamma 1, gamma 2, gamma k. Similarly, we have uh, um, gamma 1, gamma 2 and so on up to gamma k, alpha 1, alpha 2 up to alpha m are linearly independent. So that means all the scalars has to be 0. So C1 equal to C2 equal to up to Ck all are 0 and similarly A1 equal to A2 and so on up to Am all are equal to 0. So that means, so therefore S1 is linearly independent. So we have proved the first claim. So now I need to show L of S1 is equal to W. Now claim 2. I need to show L of S1. So this will span the so L of S1 is W1 plus W2. I need to show this, right? So if I show this, then this S1 is linearly independent and forms the basis for W1 plus W2 and number of elements is K plus M plus T. Therefore, both will be equal. Now the theorem will be over, right? Now I need to show that L of S1 is W1 plus W2. So whenever we need to prove equality, so we need to show contained in this and this is contained in this, right? Okay. Since W1 plus W2 is a subspace of V and each element of S1 and each element of S1 belongs to W1 plus W2. So therefore L of S1 is contained in W1 plus W2. The first part is easy. I need to show that this is contained in this. Yeah, obviously this W1 plus W2 is a subspace, right? So that means yeah, since subspace means what? By definition, all the linear combination will be in L of S1 is all linear combinations, right? So by definition of subspace, obviously L of S1 will be in W1 plus W2 because W1 plus W2 is a subspace and each element of S1 belongs to W1 plus W2. Linear combination is nothing but alpha W1 plus beta W2, right? So L of S1 is what? All the linear combinations of S1. By definition of subspace, L of S1 will be contained in by definition of subspace. Now we need to prove that W1 is contained in. Now we prove that. Now we prove that W1 plus W2 is contained in L of S1. So if I prove this, then this equality will be proved, right? Okay. Now let alpha be any element of W1 plus W2. I need to show that this alpha is in L of S1 also, right? That is, we have alpha be any element of W1 plus W2. I need to show that this alpha is in L of S1, right? Okay, that means this alpha can be expressed as a linear combination of basis of S1, right? Okay. Now, alpha alpha be any element of W1 plus W2. So that means alpha is equal to some element of alpha is equal to alpha is equal to some element of W1 plus some element of W2, right? This implies, see, some element of W1. That means this is a linear combination of a linear combination of elements of basis of W1 plus a linear combination of elements of basis of W2, right? So this implies it is a it is a linear combination of elements of S1. This implies alpha belongs to L of S1. And where is alpha? W1 plus W2. So W1 plus W2 is contained in L of S1. So let's call this as let's call this as 1. Let's call this as, so from 1 and 2, linear span of S1 is W1 plus W2, and also dimension of W1 plus W2 is equal to what? So what is the basis for W1 plus W2? So this is the basis for I have assumed. It has k elements, m elements, t elements. So k plus m plus. So which is the proof, right? So very interesting proof. So I'll repeat how I proved. So first, what I'm going to first what I've assumed is I have assumed that this dimension is k, right? I have assumed that this dimension is k. That means this basis elements has k elements. So gamma 1, gamma 2, gamma 3 up to gamma k be basis for W1 intersection W2, right? W1 intersection W2. Now this set S is linearly independent element and these all the independent elements belongs to W1. So it need not be a basis for W1. It is a basis for W1 intersection W2. So even though it is not a basis, we can extend to form a basis. So let the extended vectors be alpha 1, alpha 2 up to alpha m. What is the dimension of W1? It is k plus m. And similarly, this linearly independent vectors is contained in W2. So that means even though it is not a basis for W2, it can be extended to form a basis. So let the extended vectors be beta 1, beta 2, beta 3 up to beta t. So dimension is k plus t. So what is dimension of W1 plus W2 minus dimension of W1 intersection W2? This is k plus m, this is k plus t, this is k. So we have got k plus m plus t. Now we will prove that dimension of W1 plus W2 is equal to k plus m plus t. So I'm going to claim the set S1, which is gamma 1, gamma 2, gamma 3, gamma k, comma alpha 1, alpha 2 up to alpha m, beta 1, beta 2 up to beta t forms a basis for W1 plus W2. If I show that this says that this set is a basis for W1 plus W2, and obviously what is the dimension of this? This has k elements, this has m elements, this has t elements. So it will be as k plus m plus t. The proof will be over. Now to show that this set is a basis, you need to show this set is linearly independent and this set spans W1 plus W2. So for linearly independent, I need to multiply all with scalars. I need to prove all the scalars are equal to 0. So I have proved all the scalars are equal to 0. And for linear span of S1 belongs to W1 plus W2. So I need to show this contained in this and this is contained in this. I'm taking some element in W1 plus W2. That means alpha is some element of W1 plus W2. I can always write that as linear combination of basis of W1 plus linear combination of basis of W2. So if I combine, I can always write a linear combination of elements of S1. So that means alpha belongs to S1. So the proof is very easy, right? Okay. So we'll come to the problem point of view. We'll move on to problem, right? So problem one, very interesting proof, right? A minute. Is it clear? Consider consider the consider vector space D, which is R4 of R, and two subspaces and subspaces B. So I have two subspace W1, which is all those X, Y, Z, W, such that 2x minus y plus z is equal to 0, comma x plus y plus w is equal to 0. And I have W2 to be equal to all those x, y, z, w such that x minus 2y plus z minus w is equal to 0, comma x plus y is equal to 0. Find the find the basis and dimension for W1, W2, W1 intersection W2, W1 plus W2, right? So we're going to make use of previous theorem. Very easy, right? Okay. So first what we will do is we will find the, you know, how to see what is W1. W1 is nothing but the solutions of homogeneous system, right? And W2 is also a solution of homogeneous system. So first what we will do is let us try to find W1. So what is W1? W1 is all those X, Y, Z, W such that 2x minus y plus z is equal to 0, comma x plus y plus w is equal to 0. So W1 is solution space of this homogeneous system. So let us try to find the solution space Ax equal to 0. So A matrix is what? 2 minus 1 1. Okay, x y z w. Okay, so x y z w. So we'll form augmented matrix, right? form an augmented matrix A comma O. So X, Y, Z, W, and then X, Y, Z, W. See, here we don't have any vectors. Let us put 0, 0, 0, so that it will be comfortable for you. Now we'll make this to row echelon form. So R2 is transformed to 2 times R2 minus R1. This is equivalent to 2 minus 1, 1, 0, 0. So multiply 2 and then you subtract. You multiply 2 and then you subtract. So if you multiply 2, it will be 2, be 3. You multiply 2 and then you subtract. You multiply 2 and then you subtract 0, 0, 0, 0. Now you can see this is in row echelon form, right? In, in row echelon form, in row echelon form. And what about number of free variables? Always note that number of free variables will give you the dimension, right? Number of free variable is equal to total variable minus rank of A. Total variable is 4. Total variable is 4. Rank is 2. So we have two free variables, right? So let us assume those free variables to be equal to, so we have two free variables. So we have equations 2x minus y plus z equal to 0, and then you have 3x 3x minus y plus 2w is equal to 0, right? So we have what, how many free variables here? We have two free variables. Let us assume x to be equal to k1, y to be equal to k2, y to be equal to k2. These are just look similar to previous problems, right? So what about from 2 we have 3x minus y equal to minus 2w. So w is minus 1 by 2, 3k1 minus k2, right? So from 1 we have 2x is equal to y minus z. So y is k2 minus z. We have so from 1 we have z is equal to y minus 2x. So y is k2 minus 2 times x is k1. So z is equal to k2 minus 2 times k1. Therefore, the solution space x, y, z, w for w1 is, so x is k1, y is k2, z is k2 minus 2 k1, and w is minus 1 by 2 3 k1 minus k2. See, you can check it out. Let us put k1 k2 both to be equal to 1, right? Solution will be what? 1 comma 1 comma 1 minus 2 is minus 1. If I put k both to be equal to 1, we will have 3 minus 1 is 2 by 2, so this will be minus 1. So 1 1 minus 1 minus 1, 1 1 minus 1 minus 1. To check whether it is satisfies or not. So 1 1, that is this is x, this is y, this is z, and this is w. So 2 times x is 2, minus y is 1, yes it is 0, x plus y plus w, x plus y plus w, 1 plus 1, I think it is wrong, both are equal to 1, now plus y. Any mistake you have made? Reply to x1 Okay, okay. I think here I made mistake, right? See, we have equations 2x minus y plus z equal to 0. And then this is what? This is yzw. So 3y minus z plus 2w is equal to 0. Right? So let us assume y to be equal to k1, z to be equal to k2. So from 2 we have 3k1 minus k2 plus 2w is 0. So 2w is k2 minus 3 times k1. So w is k2 minus 3k1 by 2. And from 1, 2x is equal to y minus z. So y is k1, z is k2. So x is k1 minus k2 by 2. So our solution x, y, z, w is k1 minus k2 by 2. Y is k1, z is k2, and w is k2 minus 3k1 by 2. Now, if I assume k1, k2 both to be equal to 1, you will have 0, comma 1, comma. If both are 1, this is minus 1. Now you can check this out. X plus x, y, z, w. X plus y plus w. 0. Yes. 2 times x minus y plus z. So again it is 0. This is correct. Now, if I take k1 outside, we will have minus 1 by 2, comma 1, comma 0, comma minus 3 by 2 plus k2 times we will have minus 1 by 2, 0, comma 1, comma 1 by 2. This is a basis for so basis for w1 equal to minus 1 by 2, 1, 0, minus 3 by 2, and minus 1 by 2, 0, 1, 1 by 2. And what about dimension of w1 is equal to 2. We already know dimension of w1 here itself, right? Because dimension will give here itself we can find dimension. Dimension of w1 is 2 and the basis for w1 is the first answer. Right? Find a base dimension for w1. Now we will find dimension and basis for w1, w2, right? Okay. Is it clear? See, this is one of the bases, right? I can also take basis to be equal to, or I can also take basis to be equal to. Let us take multiply 2 with this, right? So there will be minus 1, 2, 0, minus 3, comma minus 1, 0, 2, 1. So if you want to have in simplified form, now we will find the base dimension, and for W2 we will find basis and dimension. Now what is W2? So W2 consists of all those x, y, z, w such that x minus 2y plus z, x minus 2y plus z minus w is equal to 0, x plus y equal to 0. So we'll directly write the augmented matrix A comma O. So 1 minus 2, 1 minus 1, x, y, z, w, x, y, z, w, and we will write 0, 0, 0, 0. So 0, 0, 0. So we'll reduce to row echelon form. So R2 is transformed to R2 minus R1. This is equivalent to 1 minus 2, 1 minus 1, 0. So 0, so 1 plus 2 minus 1 plus 1, 0, 0, 0, 0, 0, 0. This is in row echelon form. This is in row echelon form. So what about number of free variable? This will give the dimension of W2. So total variables minus rank of A. Total variable is 4, rank is 2. So we have two free variable. And what are the equations we have? X minus 2y plus z minus w is 0. So I'm just subtracting. Okay. And then we have y, z, w. So 3y minus z plus w is equal to 0. So let us assume y to be equal to k1, z to be equal to k2. Let's assume y to be equal to k1, z to be equal to k2. So from 2 we have 3y minus z plus w is equal to 0. So 3 times y minus z plus w equal to 0. So w is k2 minus 3k1. And from 1 we need to find x. So x is 2y minus z plus w. So 2 times y is k1 minus z is k2 plus w. So k2 minus 3k1. So 2k1 minus 3k1 is minus k1. These two will get cancelled. So x is minus k1. So therefore the solution is xyzw equal to minus k1 and y k1 k2 k2 minus 3k1. Now we can check it out. If I put k1 k2 to be equal to 1, the new solution is minus 1 comma 1 comma 1 comma minus 2, right? Minus 1 1 1 1 minus 3 is minus 2. Let us check this whether it is correct or not. X plus y is 0. This is x y z w. X plus y is 0. Yes, correct. X minus 2 times y. So minus 1 plus 2 times y plus z minus w. So this will be what? So I took y to be equal to k1 means 3k minus 3x z will get are equal to x minus 2 minus times y plus z plus z plus. Yes, correct. So our solution is correct, right? So because this satisfies this equation, right? So minus 1 minus 2 times y. It is minus 2. Can satisfies, right? Minus 3 plus 3. Therefore, the solution is correct. Therefore, you can see our solution for W2 is minus K1, K1, K2, K2 minus 3K1. So if I take K1 outside, we will have minus 1, comma 1, comma 0, comma minus 3. If I take K2 outside, we will have 0, comma 0, comma 1, comma 1. This step, so basis for W2 is equal to minus 1 comma 1 comma 0 comma minus 3 comma 0 comma 1 comma 1 comma 1. This is these two elements will span the entire solution space for W2, right? For W2. And what about dimension of W2? So it has two elements in the basis. Dimension of W2 is, right? Okay. Is it clear? As of now, we found dimension of W1 and basis for W1. Also, we have found dimension of W2 and basis for W2. Now, what we'll do is we will find for W1 intersection W2, right? So, W1 intersection W2 consists of all those x comma y comma z comma w such that the solution should satisfy W1 as well as W2. So that means it should satisfy all four equations. Yes or no? 2x minus y plus z equal to 0, x plus y plus w has to be equal to 0, x minus 2y plus z minus w has to be 0, and x plus y has to be equal to 0. Is it clear? I need to find all those x, y, z, w that satisfy both W1 and W2. So that means it has to satisfy all four equations. Now we will find the solution. We will find the basis and dimension for W1 intersection W2. So again we will form AX. We will form an augmented matrix. So we will form an augmented matrix A comma O. So this is X Y Z W, X Y Z W, X Y Z W, X Y Z W. So we will reduce this to row echelon form, right? We will reduce to row echelon form. Now we'll reduce to row echelon form. So first what we'll do is we will shift R2 and R1 so that it will be easy for us to reduce to row echelon form. So if I shift this, we will have so 1 1 1 1 0 1 0, 2 2 minus 1 1 0 0, 1 minus 2 1 minus 1 0 1 1 0 0. Okay, so you will have R2 is equal to R2 minus 2 R1. R3 is transformed to R3 minus R1. R4 is transformed to R4 minus R1. So this means this is equivalent to 1 1 0 1 0. So multiply 2 and then you subtract. You 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 will have 0. So 1 minus 1 is 0. Minus 2 minus 1 is minus 3. 1 minus 0 is 1. Minus 1 is minus 2. And then we have 0. So 1 minus 1 is 0. 1 minus 1 is 0. 0, 0, 0. Right? Now R3 is transformed to R3 plus R2. So this is equivalent to 1 1 0 1 0, 0 3 1 minus 2 0, 0 0 0 0 0, 0 0 0 0 0. So this is in row echelon form, right? This is in row echelon form. And what about the number of free variable total variables, total variable minus rank of A? Total variable is 4, rank is again 2. Again it has two free variable. That means dimension of W1 intersection W2 is also equal to 2, right? Let's try to find solution of all. So we have x plus y plus z plus w equal to 0, and then we have x corresponds to y, this corresponds to z, this corresponds to w. So 3y plus z, 3y plus z minus 2w is equal to 0. Again we have two free variables. Let us take y to be equal to k1. Let us take y to be equal to k1, z to be equal to k2. So we will find x, y, z, w now. So from 2 we have 3 times k1 plus k2 is equal to 2w. So w is equal to 1 by 2, 3k1 plus k2. And from 1 we have x is equal to minus y minus w. So minus y minus w So minus k1 minus 3k1 by 2 minus k2 by 2. So minus 5k1 by 2 minus k2 by 2. So which is minus 5k1 minus k2 by 2 for x. Therefore, solution space for W1 intersection W2 is given by x comma y comma z comma w is equal to, so x is minus 5k1 minus k2 divided by 2. So y is k1, z is k2. So w is 3k1 plus k2 divided by 2. You can check this out. If I take k1 and k2 both to be equal to 1, you will have solution to be minus 5 minus 1 minus 6 by 2 is 3, and 1 comma 1 comma 3 plus 1 is 4, 4 by 2 is 2. So minus 3 1 1 2 minus 3 1 1 2. Let us see it satisfies all four equations. 2 times x, 2 times x minus y plus z. Is it correct? So w1 x comma y comma z, x y plus z equals to x plus y, x plus y. Z. X is x is so if one take minus x, it is not satisfying. Whether I made mistake anywhere. I think I made mistake somewhere. Can you please check this out? Can you please check this out? I made mistake. X minus Yes, yes. Sorry, I think I'm wasting your time. R2 minus 2 R1 minus 1 minus 3, right? Minus 1 minus 2. Sorry, this is minus 3. I think it is minus 3, right? Sorry, I think I wasted your time. So minus 1 minus 2. This is minus 3. See, this is minus 3 again. See, 1 minus I made an entire sum wrong. Minus k1. That means minus 3k1 minus 3k1 will be plus 3k1, and this will be minus 2k1 plus k1. So this will be minus 2k1, k1 by 2. So k1 minus k2 by 2. This is your x. K1 minus k2 by 2. Now, if I take, let us see now whether it is correct or not, right? Let us take k1, k2 both to be equal to 1. So we will have 0, comma 1, comma 1, comma 2, right? We take k1, k2 both to be equal to 1. So 0, comma 1, comma 1, comma 2. 0, comma 1, comma 1, comma 2. So 2x minus y plus z. So this is x, y, z, w. 2 times x minus y. X, it is correct. And then we have x plus y plus w. W is minus 3k1 plus k2. Yes, so if I take this as 1 1, so we will have minus 3 plus 1 will be minus 1, right? Minus 3 plus 1. Okay, that means this is 0, comma 1, comma 1, comma. So x, y, z, w. Okay, I think I'm making some mistake, right? So what I'll do is in the next class I will continue with diamond W1 plus W2, right? So the next class I'll continue with W1 intersection W2. So that's it. So we'll stop here. So next class we will do continue dimension W1 intersection W, right? That's it. So thank you. All the best. Bye.